Hi all, welcome to module 12. We're going to talk about scaling a database. So we need to scale a database when we need to increase the amount of load that our database can handle. This usually happens when the amount of data that is being generated by the activity on the web app starts growing rapidly, or when the activity on the app requires many more queries to be handled by the database. The typical signs of knowing when we need to scale a database are when performance starts suddenly degrading rapidly. So whenever additional users come on, the performance just suddenly drops. We also know that it's time to scale the database when the resources are very frequently near maximum use. For example, the CPU, RAM, or disk is maxing out. We can also predict that we need to scale when the data is growing extremely rapidly and we can see that we would run out of resource very soon. So the first thing to do when we're presented with a scaling problem is to do research. We should not make any assumptions about what is affecting our database performance and what the right way to scale is. We need to monitor key metrics, study the database system logs, and do this whole process scientifically before we draw a conclusion of which method should be used. So typically we should be analyzing the queries and the query performance, and we should be looking at the CPU, RAM, and disk health of our database server. The first thing to do is to tune our database for increased performance. We've already discussed this in one of the previous modules. The idea behind increasing the performance is that if we're able to make each query on the database run faster, then we can perform a greater number of queries every second. The three main things that we've already discussed that can be done is that number one, queries can be improved, and we can do this by studying the query plans and the database logs. The second thing is to add indexes or remove constraints or to alter some of the structures in the schema to increase the read or write performance of the database. The third thing to do, which is the hardest to do in this list, is to modify our schema to better suit the common queries that are being made on the database. Once we realize that it's becoming too hard for us to tune the database for greater performance, the next thing to typically do is to vertically scale the database server. And by database server here, I mean the hardware that the database server is sitting on. So the three kinds of things that are done are improving the disk, the RAM, and the CPU capacity of the particular machine that the database server is on. And improving the disk means either increasing storage capacity in case we're running out of disk space, or to increase the number of I/O operations per second the database can do. For example, going in for an SSD over a hard drive or going in for a better SSD. The next thing to look at is typically the memory or the RAM. DBMSs use RAM very effectively because they cache a lot of stuff. For example, indexes are cached by the DBMS so that the DBMS does not have to make a disk request to fetch the index and then a disk request to fetch the data. The index is already in RAM, so the database just has to search through the index and then make a disk request to fetch the data. Increasing the CPU could mean two things. Could mean making each core faster, or could also mean increasing the number of cores that we have. Both of these have a different impact depending on the DBMS. Typically though, for most database systems, RAM and disk provide the greatest amount of benefit, and the impact of improving the CPU configuration is heavily dependent on the DBMS. The next step to scale the database is using Masterslave scaling. We talked about Masterslave replication for backup, but more important than its backup use case is its use in scaling. Also, using a Masterslave for backup as the exclusive method for backup is actually a little dangerous, because if human errors are made on the master, then they will also propagate to the slave. But coming back to scaling, we typically look at master-slave scaling when the write traffic is getting a little heavy and the write traffic has started to affect the read performance of our database. So the way it's typically set up is that we have a master database and a slave database. The slave is getting changes and staying up to date with the master database. So we write to the master database and then we make all the read queries on the slave databases. So this is what the setup looks like. We have a web app on the left, and the web app is making a write query to a database instance, which is a master. Changes from the master are propagated to the slave databases automatically. These are copies of the master database, and the web app does not make read queries from the master database, but it makes the read queries from any one of the slave databases. This actually provides us a way to keep scaling the number of read queries that we need. So if we want to increase the number of queries that we can support for read, we can just add more and more slave databases. The last broad methodology for scaling is called sharding. Sharding is pretty much the scariest way of scaling databases, and it should only be attempted in the case that the application really needs it. Sharding is a process of splitting a large data set on a single database into smaller shards across several database instances. And this is only done when one particular database instance is not able to handle the entire write traffic. Sharding, or breaking up the data into various shards, is a process that can be done manually or automatically. So we can split the data according to how the data is being used across different instances. We can also use DBMSs that support sharding out of the box. Examples of some database systems like this are MongoDB. These database software are fairly complicated and sophisticated pieces of code because they solve fairly hard distributed systems problems. They typically end up sacrificing on some traditional properties that we expect of a database to be able to achieve sharding in a cluster. For example, transactions may not work across a cluster, or reads might not be immediately available after writes or updates are made to the database. Sharding is hard because of two reasons. The first reason, which is fairly obvious, is that applications need to change the way they work. For example, applications might have to make requests for reading or writing data to different shards, or they might have to handle transactions in the application logic because the database cluster cannot handle it anymore. Sharding is also hard for a more subtle reason, and that reason is that backup, recovery, and migration also become very challenging because the data is not in one database instance anymore, but it's split across many shards. So the two broad ways of sharding are sharding data by usage, so we can take tables that are being used more frequently than other tables and take them out and put them into separate database instances, or we can shard by key, in which case data inside a table is split across various database instances. So depending on the value of a key, a row is put in one database instance or another. For example, if we are looking at a user table, then we might decide that all the users from 1 to 1 million go into shard 1, from users 1 million to 2 million go into shard 2, and so on and so forth. To quickly summarize the concepts that we learned in this module, we understood that we should approach database scaling very scientifically. We should start with all the simple stuff that we can do first. Master-slave replication is a method for scaling and for splitting read and write traffic. It works very well when the write traffic is not extremely high and the read traffic is increasing. Sharding is one of the final ways of scaling and handling the largest amount of data. Sharding, although solves the scaling problem to some extent, is one of the hardest things to implement and get right.